Good day and welcome to the pre-practical lecture for Experiment 2, a kinetic study of the reaction of persulfate with iodine. We know that different chemical reactions take place at different rates. For example, if you look at the reaction between silver nitrate and potassium chloride, the formation of silver chloride is almost instantaneously. Compared to the formation of ammonia gas from hydrogen and nitrogen gas, which is a very slow reaction, especially at room temperature. So kinetics is then the study of the rates of chemical processes in an effort to understand what it is that influence these rates, and then to develop certain mathematical expressions which we can use to predict the rates of chemical processes. So the principal goal of any kinetics experiment is to deduce how the rate of a reaction depends on the concentrations of the species involved. And here the species that I talk about can be reactants or products. And then the resulting mathematical expression that we obtain from experimental data is called a rate law of a reaction. We will talk about that in much detail when we do the theoretical part right at the end of the course. Please just remember that the rate law can only be determined by experiment, so you cannot use reaction stoichiometry to determine the rate law of a reaction. You also know that reaction rates might depend on different experimental conditions, for example, the concentration of your reactants or products, the pressure if you have gases forming or gases being consumed, and also the temperature of your reaction mixture. And we can optimize the rate of a reaction by choosing appropriate experimental conditions. Why do I then want to study chemical kinetics? What is the industrial importance of studying the rates of chemical reactions? So we study rates of chemical reactions to determine the conditions under which reactions can be made to proceed at favorable rates. Also, it can give us key information on the reaction mechanism. What do I mean by a reaction mechanism? That is the sequence of steps by which reactants are converted into products. So an understanding of the reaction mechanism can enable us to adjust the conditions in order to produce a product at a desired rate. And it can also increase our understanding of how chemical reactions occur at the molecular level. In the end, all of this together will enable us to control chemical reactions better and to manufacture chemical products in the most economical way. I'm now going to move forward to the theoretical aspects related to Experiment 2. Please read through section 2.2 in the practical manual for this experiment. So there's section theoretical considerations. I am just briefly going to mention a few things which I think you might have trouble following from the practical manual, but in the manual there's comprehensive explanation of some other aspects which you will also need. So which reaction are we going to study in this experiment? We're going to look at the reaction of iodide with persulfate in an aqueous solution, and we're going to form iodine and sulfate. So the rate equation for the reaction is given here, and I'm giving it as a derivative. So it's negative the change of the persulfate concentration with time. And we will also talk about this in much detail when we do the theory, but I just want to talk about the left-hand side of the rate equation first. The negative sign there stems from the fact that your persulfate, your S2O8 negative, is being consumed in your reaction. So that is a reactant. So the reactant is being consumed, and therefore we've got a negative change in the concentration of the reactant with time. I will also not refer to stoichiometry here because I don't want to confuse you, but later on when we do the theory, I will briefly mention aspects related to stoichiometry. So for now, what you need to know is that the expression that's given on this slide gives you the rate equation. So it's the change in concentration of the reactant with time equals a mathematical expression K, which is the rate constant, times the concentration of the persulfate to the power N times the concentration of iodine to the power M. So M and N will be determined experimentally, and this is what you're going to do in this specific experiment. How do I get the values of M and N? From the above mentioned information, you're going to study the change in concentrations of the two reactants with time at a constant temperature. Why do we keep the temperature constant? Because we know that reaction rates depend on temperature. So you are therefore going to work in a constant temperature water bath, and therefore you're going to control the temperature of your reaction system. So how do I follow the progress of my reaction? My persulfate will react with iodide to form iodine and sulfate anions in solution. Now, in aqueous solution, iodine can react with iodide to form triiodide ions. So this reaction is given here. Triiodide is known to form a dark blue-black complex with starch. And we can use this as an indicator to test for the presence of iodine in our reaction mixture. However, there is a problem because this complex is not water soluble, and its formation at high concentrations of iodide may interfere with a kinetic analysis. So what do we do as a solution? We are going to perform another reaction. So we're also going to add a known quantity of thiosulfate to keep the iodine concentration constant throughout until we are close to the end of the reaction. So what we do is you add thiosulfate, that will react with iodine. I'm forming iodide again and tetrathionate. So if you compare these two reactions, what I'm basically doing is to consume the iodine that I form, keeping the iodine concentration low. If that is low, it means I won't form the triiodide and it won't form the complex with starch. Okay, so the moment all my thiosulfate is being consumed, so all of it has been used up, I will allow the formation of iodine again. If I allow the formation of iodine, it will react with the iodide. I will have triiodide, and then I'm going to have a color change. So I have a limited but also known quantity of the thiosulfate. And you will see in your experiments that you're going to add the same quantity of thiosulfate for all your reaction mixtures. So in summary, I've written down both reaction equations here. So the reaction you want to study is equation 2.1 from your practical guide. So it's the reaction between persulfate and your iodide. I want to limit formation of iodine, and therefore I'm going to react my iodine with a known quantity of thiosulfate. When all the thiosulfate is being consumed, I will allow the formation of my iodine again, and then I will have a color change. Because I add the same amount of thiosulfate to all my reaction mixtures, I am going to measure the color change almost as a yardstick. So for all my experiments, will run to the same extent until the color change, and that is the time that you will measure. So you will measure from when you add your reactants together to the time of the color change, and because the same quantity of thiosulfate has been consumed at that time, it means that I can follow my experiment to the same extent. So in your experiment, you're going to vary the initial concentrations of your two reactants, and you're also going to vary the temperature and then determine the time it takes for a color change at these varying conditions. So how do I determine the rate equation? Rate equation is given here from your practical guide as equation 2.2, you need to experimentally determine the values of m and n in this expression, and that will give you your rate equation. And m and n are called the reaction orders with respect to the two reactants. And they can be determined from the initial concentrations of the reactants combined with the time it took for the color change to be observed in your experiment. I'm going to show you an example of how to do that on the next slides. But first, before you can do that, you will need to know the initial concentrations of your reactants. And you will have to calculate your initial concentrations for each experiment. You will see that you have different reaction mixtures that you're going to make up. You need to calculate your initial concentrations for each experiment before you come to the laboratory. So please, this forms part of your preparation for the experiment. And you will use the volumes and the concentrations of your reagents used. So you're going to make up reagents with specific concentrations. I've given you the concentrations here. It's also given in section 2.3.2 of the practical guide. And for each reaction mixture, you're going to use a different volume. So volume and concentration you can use to calculate the moles of your reactant, combined with the total volume of your reaction mixture. The total volume will be the volume after you've added everything together. You're going to see that for all your mixtures, this will be 50 milliliters. So you will have moles divided by volume. Okay, and that gives you the initial concentration. Please do these calculations before you come to the laboratory so that your practical demonstrator can double check your calculations for you. You're going to use the equations given on this page to determine the rate equation. I've again just copied equation 2.2 or the rate law from the previous slide and from the practical guide. Then you also have an equation 2.10 in your practical guide, and the Hendrik has given us equations 2.10a and 2.10b, which is just extensions of equation 2.10. So these simplify calculation then of your rate expressions. So to determine your reaction order, you are going to use these two expressions. So you will use the ratio of the times for two experiments. So say you study experiment 1 and 2, you're going to use the ratio, the time for experiment 1 over the time for experiment 2. And then you will use the ratio of the persulfate concentration, but it's the persulfate concentration of time 2 divided the persulfate concentration of time 1, all to the power n. Okay, but when you use a set of experiments, the concentration of your other reactants should remain constant. So you can only use this ratio if, in this case, the iodide concentration between experiment 1 and experiment 2 remained constant. So make a huge mental note of that. I will also repeat that when I show you the example of the calculation. Also note that here you've got an inverse relation. So you have time 1 divided by time 2, and here you've got concentration 2 divided by concentration for experiment 1. And that is because your rate is inversely proportional to time. Okay, so remember when you did a first year kinetics, you calculated the reaction order in a similar way, but you used initial rates. So you used a ratio of initial rates to the ratio of initial concentrations, and you determined your reaction orders. So if you're slightly confused now, go back to your first year textbook and just look at that example of where you used initial rates to determine reaction order. But this is the rate expression, and it says rate is negative the change of reactant concentration with time. So your rate is inversely proportional to time. And that is why I'm switching. I don't have T2 over T1. I have T1 over T2. So rate inversely proportional to time. So I can determine N here by the ratios of the concentrations of experiment 2 to experiment 1. And then I can do the same for my other reactant. So when I determine the value of M, or the order in terms of my iodides, remember that I must choose a set of experiments where my persulfate concentration remains equal, and then I can look at the effect of only changing the initial concentration of the iodide and look at the corresponding change in the time. So I will show you a specific example in the next slide. So this is our example now. I've just made up data for this table, so please, there's no correspondence to your experiments. It's completely different, and the values of the concentration should also be completely different from what you've got. So you're going to have a table. I think you have 5 mixtures, but your table of data should look more or less like this. So you will have different initial concentrations. So this is the concentration that we're referring to here. These are your initial concentrations of your 2 reactants, and the time is the time that you are going to measure yourself. So to determine the order then, if you look at experiment 1 and experiment 2, and I look at the initial concentration, my iodide concentration remains constant. So that means the time difference, or the variation in time for the 2 experiments, is dependent on the change in the initial concentration of my persulfate. Okay, my iodide concentration did not change between reaction 1 and reaction 2, so the dependence of the time, or the duration of the experiment, was due to the change in the initial concentration of persulfate, and I can use that then to determine the order of the reaction with respect to the persulfate. Okay, so if I now go and I use my equation, I say the time for reaction 1 divided by the time for reaction 2 is then equal to the ratio of the concentrations of reaction 2 over reaction 1 to the power n. So I substitute from the table. If you want to double check, you can pause the video here and just double check for the substitutions. Remember, 320 seconds relates to a concentration of 0.3. Okay, so 320 relates to a concentration of 0.3. and 110 seconds relates to concentration of 0.9 to the power n. So when I simplify that, I get 2.9 is 3 to the n. So the easiest way to solve the mathematics here is to take the ln or the log left and right hand sides for both. Log of 3 to the n equals n log 3, and from that I can easily calculate the value of n. We are going to always assume that our reaction orders are integer values. Okay, so if you get 1.1, you're going to round it off to 1. If you get 0.97, you're also going to round it off to 1. Okay, so reaction orders can be non-integer values, but we are not going to do that now. We will just assume integer values. Okay, so you can go try this yourself. Then please do the calculation for iodine. For iodine, the iodide, you are going to use experiments 1 and 3. Because if I look at experiment 1 and experiment 3, the concentration of my persulfate remained constant, and the concentration of my iodide varied. So the change in the time, or the variance in time, would be due to the variance in my iodide concentration, because the persulfate concentration remained constant. So please go repeat this calculation, pause the video and see whether you get this value for M, and then also first order in the iodine. And this would be the way that you treat your experimental data as well. Double check that the other reactant concentration remains constant. So why do we repeat our experiment at different temperatures and in different water baths? We know that the reaction rate depends on the temperature. That means that the rate constant will also be temperature dependent. The calculation of the rate constant at a specific temperature is explained in the practical guide. and that's also explained in your Experiment 2 Kinetics post-practical lecture. So please watch that video for an explanation on calculation of the rate constant. Now, the temperature dependence of the rate constant is given by the Arrhenius equation. So Arrhenius equation says that the rate constant, so the symbols here just means rate constant K, which is temperature dependent, equals the pre-exponential factor A times the exponent of the ratio of negative activation energy divided by RT. So EA is the Arrhenius activation energy, that is the energy required to start your reaction. And then R is your gas constant. You should use 8.314 joule per Kelvin per mole because you're calculating energy here. And then temperature always in Kelvin. So if I take this equation and I take the ln of that equation, I get the equation on the right hand side. And now I'm going to plot ln K against the inverse of temperature, and then from the slope I'm going to get negative activation energy over R. Because I'm plotting ln K against the inverse of temperature, and the slope will be given by the quantity negative EA over R. And from this, because you know the value of the slope and you know the value of your gas constant, you can calculate the activation energy of your reaction. So by varying the temperature of our experiment, we can use this equation and obtain the activation energy. You will also be required to calculate the values of the enthalpy, entropy, and Gibbs energy for this reaction. And these calculations are all explained in the practical guide in section 2.2.4 and also in the post-practical lecture. So please refer to that for methods on how to calculate these quantities. Just a few notes on your experimental setup. Your setup will include 3 water baths held at temperatures of approximately 25, 40, and 60 degrees Celsius. Remember to note your precise temperature of your water bath. So you will need to measure that yourself. You will need a stopwatch, and please, you need to provide your own. It will be the easiest to just use your cell phone. And then you will also be equipped with general laboratory glassware. You will be required to make up a number of solutions, so these are listed on this slide. Please do your calculations and double check that you know exactly how to make up your solutions, otherwise you waste too much time in the lab. Your tutors will also double check your calculations. Read through the procedure and the practical guide. Please be well prepared and make sure to watch your experimental video for this experiment. Just a few last things. Your kinetic analysis will definitely improve by making up your solutions precisely, by accurately measuring the volumes of your mixtures, and then by performing exact time measurements. It's really much simpler and easier to work with the data if you work carefully in the lab. Please note that you need to stir well and note the initial time reading for each mixture. So you need to make a reading for time 0 when you add your persulfate solution. And then also make good use of the provided fill-in sheets. Work continuously. Please do not waste time. This experiment does take quite long and you only have 3 hours in the laboratory. So prepare well. Split the work between group members. There's no reason that all of you should do the work together. So just split the work between the group members. And double check with your demonstrator that you've got all the data you need to compile your report. Please also watch the experimental video before coming to the lab, and remember to complete the pre-practical test in ClickUp. Thank you for watching. We're looking forward to seeing you in the lab to perform this experiment.